Okay, so these paramagnetic fields, they at
सर बस
very,
स्लाइड शेयर कर दें.
एक मिनट, स्लाइड शेयर नहीं हुई, लेट मी चेक. अच्छा. Okay, so these paramagnetic materials, these paramagnetic materials, these magnetic moments inside the material, because of the electronic spin, they try to orient themselves in the direction of the external magnetic field, and they do this reorientation very, very weakly, very, very subtly. Okay, so that's why we call them as paramagnet, because they do not show magnetism. They show very weak magnetism. On the other hand, in ferromagnetic materials, this reorientation is very, very strong. So the susceptibility is very high. So zeta m is very high for these materials. Okay, so so these the mu r is very high. Mu r is very high for these materials, right? V equals to mu naught mu r h. Mu r for these materials is very high. Okay, mu r is very high for ferromagnetic materials, because why? Because the if you apply external magnetic fields through them, the material will collect those magnetic lines of forces and will provide maximum space for those magnetic lines of forces. Or in other words, the those domains, in which the material electrons were spinning around, they try to reorient themselves maximally in the direction of the external magnetic field. Okay, so that's why these materials are very strong, because their internal electronic spin reorients themselves to the direction, in the direction of the external magnetic fields. Or in other words, in simple words, I would say these materials favors very strongly the external magnetic field. That's why they are very strong magnets. Okay, so the alignment is very good in ferromagnetic materials. In ferromagnetic materials, the difference from the ferromagnetic and ferromagnetic is that most of the domains will align themselves in the direction of the external field. However, there will be very few domains which are opposite. Most of them will be aligned, very few will be in opposite direction. Okay, most of them will align themselves, very few will go anti-parallel. Okay, so such materials are called as ferromagnetic materials. There's another one called as anti-ferromagnetic materials. Okay, so this is how this phenomenon is really called as magnetostriction. If the internal atomic spin, which creates internal magnetic moment, if that aligns itself, to the external magnetic field strongly, you get a very strong magnetism. And this is the characteristic of ferromagnetic materials. But if the internal aligns itself very weakly to the external field, it will show weak magnetism, those materials, and they will not be attracted by um, the magnetic forces. Okay, so so here are the few graphs. Just go through them and try to understand these different magnetic materials. Another chart here, which again is classifying the different magnetic materials. In the diamagnetic, B inside is less than B outside. So which means diamagnetic materials are going to reduce the external magnetic field. They are going to reduce external magnetic field. So meaning in the diamagnetic materials here, in the diamagnetic materials, in these materials, look from the south, north, it's in this direction. South and north is in this direction. The external field is in this direction. So the diamagnetic materials are going to cause the diamagnetic materials or reorient themselves in opposite to external magnetic field. So they try to cancel the external magnetic fields. But again, remember, very weak. Okay. So that's why they are diamagnetic materials. In the in the paramagnetic materials, they're going to be aligned itself, but very weakly. Okay. They're going to align themselves to external field, but very weakly. Okay. So in the diamagnetic materials, the inside magnetic field is less than the outside because it's canceling the external field a little. Mu r is negative. Mu r is less than 1 in this case. And see, in the paramagnetic materials, they try to align themselves. B inside is little bit greater than the B outside. Mu r is very little bit higher than the 1, little bit, right? In the ferromagnetic material, B inside is very, very large in comparison to B outside. So mu r is very large. Okay. This alignment, they align themselves to external field. This alignment effects only occur at a temperature below the Curie temperature. Curie temperature is that temperature at above which the material will lose magnetism. Okay, in antiferromagnetic materials, B inside is nearly equals to B outside because some will align, some will cancel, some will align, some will cancel. Usually at low temperatures, nearly, remember nearly. There will be a little bit difference. Then usually paramagnetic above the transition temperature called as the Néel temperature. So this alignment, this characteristic will exist up to Néel temperature. Above the Néel temperature, the antiferromagnetic material will lose its magnetic characteristics. Okay. So and then you have the ferromagnetic materials. In the ferromagnetic materials, B inside is higher than the B outside. Okay. The ferromagnetic material, B inside is, so they still are producing, because most of the domain will align themselves, but very few will misalign, will anti-align themselves to the external fields. Okay. And then we have the supermagnetic materials. By supermagnetic, they are from the superconductors. Okay, superconductors. You know that as you lower down the temperature, the resistance of the conductor is going to decrease. So there will be very, very low temperature where you get the zero resistance for those materials. And those materials become superconductor. For example, if you put a metal in liquid nitrogen, the metal may lose its resistance, and effectively the resistance may reach a zero value. So the conductor will become a superconductor if it loses all the resistance. And that will occur at extremely low temperatures, like minus 130 degrees somewhere. And this may occur in liquid nitrogens. And so just check the temperature of the liquid nitrogen, what is that, and check how it will affect the resistance of the materials to make superconductors. Some more charts about the materials. Zeta M is given here. You can see that uh, zeta m zeta m is mu r minus 1. Zeta m is the susceptibility, mu r is the relative permeability. For iron, it's very high, like 3000. There are some paramagnetic materials for which it's a little lower values, right? And then we have the diamagnetic materials for which this susceptibility is even negative, on the negative side. But for ferromagnetic materials, it's like in thousands. Very strong magnetism for these materials. So go find out a few more. There's one more topic, that is the magnetic boundary condition. We're not going to derive these boundary conditions, but just go through them. Remember, we saw D in electric fields, we have B in the magnetic fields. Okay. You remember when you have dielectric 1, when you have dielectric 1 and dielectric 2, at the boundary between the two, the tangential component was E tangential 1 was equal to E tangential 2. Okay. Now, when you have a boundary between two magnetic materials and you are looking for the magnetic fields conditions, so B normal 1 will be equals to B normal 2. Okay. In the electrostatics, E tangential 1 was equal to E tangential 2. In the magnetostatics, B normal 1 equals to B normal 2. Here in this, in the electrostatics, D normal 1 minus D normal 2 was equal to rho S. Here we have H tangential 1 minus H tangential 2 equals to K, surface current density. That was the surface charge density because charges were static. Here it is surface current density. So see, and if this surface, if K is 0, then E tangential 1 equals to H tangential 2. H tangential 1 equals to H tangential 2. So very similar boundary conditions that you've gone through the boundary conditions of the electrostatics. I hope this is easy. So go through it and understand this lecture very generally. It's about the behavior of the magnetic materials. This lecture was about the behavior of the magnetic materials. Go through it very generally and understand it. Go through specifically these tables and try to understand the behavior of the magnetic materials. Okay. So next time we will cover very important concept in the electromagnetics, that is the time varying electromagnetic fields, a very important concept in the EMFT.
सर ये अभी तक चैप्टर 8 आप करा रहे हैं ना?
हाँ नहीं, चैप्टर 9 के कुछ टॉपिक्स मैंने कवर कर लिए। चैप्टर 9 से मैंने ये टॉपिक कवर किया है। चैप्टर ये जो टॉपिक था ना, एक मिनट, ये जो टॉपिक था ये इंडक्टेंस वाला, ये चैप्टर 9 से मैंने पिक किया है। और ये जो कॉन्सेप्ट है ना, ये वाला जो इंडक्टेंस, ये चैप्टर 9 से पिक किया था। और ये जो है ये भी चैप्टर 9 से मैंने पिक किया था। सो जस्ट टू मेक अ कनेक्शन, ओके, जस्ट टू मेक अ कनेक्शन। सो नेक्स्ट टाइम हम इसको, क्योंकि अब हमने यहाँ पे देखिए ये स्लाइड बहुत ज्यादा इंपॉर्टेंट है। यहाँ पे हमने, जैसे मैंने आपको बताया ना, मैग्नेटोस्टैटिक की कंडीशन, इलेक्ट्रोस्टैटिक की कंडीशंस हमें लीड कर रही है टाइम वेरिंग इलेक्ट्रोमैग्नेटिक फील्ड्स की तरफ,
सही,
टाइम वेरिंग ईएम फील्ड्स की तरफ। सो अभी हमारा नेक्स्ट लेक्चर टाइम वेरिंग ईएम फील्ड्स के ऊपर है, ठीक है। तो प्रॉबेबली आई विल ट्राई टू कवर दैट इन वन लेक्चर, और ज्यादा से 2 लेक्चर्स हमारे लग जाएंगे, तो प्रॉबेबली हम टीआरडब्ल्यू की क्लास ले लें तो उसको कवर
सर
कर
बात
लें।
सुनिए
जी जी
सर, आपने बायो सेवर्ट लॉ पढ़ा दी है?
जी जी जी, वो तो
ओके सर।
हम लास्ट वीक में नहीं कर चुके थे, लास्ट वीक में आई गेस हमने कराया था।
यस सर।
जी ठीक है, ब्रीफ कराया था, वेरी ब्रीफ कराया था, जनरल कॉन्सेप्ट हमने उसका कराया था, ठीक है।